Hello there, astronomy students. Dr. Shragi here, and we are moving on now to section 8.3 of your textbook, which is called The Age of the Solar System. This broadly fits into the goals of the class that are about understanding how the solar system formed and when it formed and so on, before we start moving on to some interesting activities and interesting information about each of the planets. So, all right, so today we're going to be learning about the age of the solar system, and the answer is 4.5 billion years. All right, well, that's it for today. No, of course not. Obviously, we have to follow this up with the question, how would we possibly know that? I mean, that's in fact the more interesting question is how would we actually come to know how old something like the solar system would be? All right, well, it's kind of an interesting cross connection between astronomy and astrology. Astrology. Oh my gosh, I'm the one who did it now. Astronomy. That we find the oldest rocks in the solar system and we date them. We figure out how old they are, and that kind of puts a limit as to can't the solar system can't be newer than that. Can't be newer than the oldest thing we can find in it. So we're going to have to figure out how to find old rocks, and we're going to have to figure out how to date them. Um, Figuring out how to date something like a rock is actually not terribly easy because it isn't like you atoms don't age. Okay, it isn't like somehow whether a young calcium atom looks different from a very old one. These rocks are made up of you see in the background here are made up of lots of different kinds of atoms, and um, they're all very old. Anything that isn't hydrogen and helium was created after the Big Bang, but I mean it's still billions of years old. You can't really tell by looking at a particular atom of potassium or something in one of these things how old it is. Um, Rather, we have to take a look at how many atoms of different types there are, and we can then start figuring out how radioactive materials in those rocks have decayed over time. See, some of the atoms in the rocks will be of different types of rocks that can decay. And when they decay, into a new material, we can figure out by how much of that new material there is or how much of the original old material we lost, we can figure out how old the rock is. Um, this whole process is a key vocabulary word in the goals of the course called radiometric dating. It's going to be the process by which we measure the rock's age based on radioactive decay of certain isotopes in the rock. But there's an interesting idea here that I remember as a kid being confused about, and this is the whole idea of what is a rock's age? I mean, the rocks in the background here, they're pieces of an older rock. Does that mean like we reset their age? They might have been weathered. They might have been through the rock cycle if you took astronomy, earth science. What do we mean by the age of a rock? And in the context of these kinds of experiments, what we mean by the age of the rock is how long it has been since the last time that rock solidified. Remember, all rock was at one point molten. If it's part of the Earth system, it was, an igneous rock at some point. Um, Even if we've weathered it down into sediments and made it into like a sedimentary rock or something, and if you're a survivor of the earth science class, it hasn't resolidified. It's been the same little grains of feldspar and uh, granite or mica and all these good things, right, for all that time. Even if we're talking about something that's not on Earth, like a piece of an asteroid or something like that, when they impacted and formed this asteroid, there probably the heat of the impact produced melting, and the melting at that time, well, like resets the clock on the age of that rock. Okay, so basically, when we're talking about the age of a rock, we mean how long it's been since the last time it was liquid, the last time it solidified. Because yeah, I mean, if they go through the rock cycle, there'll be lots of changes, but it's only if we actually melts and goes back into igneous state that like kind of resets the clock here. Okay. So what we're going to be looking for on Earth is rocks that are very old and maybe have not been weathered and gone back into the rock cycle for very long periods of time. Hopefully, since early in the Earth's history. Well, frankly, finding things like that is not going to be easy. All of these rocks are going to be made up of lots of different elements. Um, in the earth science class, we already had learned, these are clearly different kinds of sedimentary rocks. And well, actually, it looks like there's There's igneous rocks in there. I don't know why I just got this piece of clip art someplace. There are going to be all kinds of minerals in here. All the minerals are made up of all different kinds of atoms, and frankly, the atoms are made up of different, come in a variety of different isotopes. Remember that word isotopes? We learned about that a couple weeks ago in the class. Remember, let's just pick an element. How about iron? Iron comes in several different isotopes. All iron has the same number of atoms. Let's forget iron. Let's do carbon, just because I happen to know. All carbon has 6 uh, protons. That's what makes it carbon, is it has 6 protons, but it can have different numbers of neutrons and in its nucleus. And so you can have different types of carbon. They're chemically the same. They work the same way in the atoms and stuff like that there, but they have different nuclear properties. And one of them is that not all of these different isotopes will be stable. Some of them will, over long periods of time, decay. We would say that some of these isotopes are radioactive. In the case of carbon, it's carbon 14 is radioactive. It decays into some other element at a known rate. I don't remember late at night and I haven't slept. I can't remember right now what carbon 14 decays into, but over long periods of time, carbon 14 decays. That's how you carbon date or radiocarbon date, um, living things and recently dead things and so on. Well, carbon 14 doesn't have a particularly long time to decay. It's only a matter of a few thousand years. That's not enough for us to be checking in these rocks. But these elements of some of these isotopes of these elements will decay. At a fixed rate, these atoms have a certain probability to decay. At first, they'll decay relatively fast. A large number of the atoms of, let's say, iron or potassium or whatever will be decaying into whatever their daughter product is. We'll learn that term in just a little bit here. And after a while, though, it gets slower and slower and slower. Each atom will have a chance of breaking down into a different element. What your book is using as an example of a way to do radiometric dating of rocks is a particular isotope of potassium called potassium 40. The symbol for potassium you can see over here is K. I have no idea why it's K. I think it's because it's calc in German. I'm not sure. Anyway, potassium has 19 protons and a total atomic weight of 40, so it must have 11 neutrons in there when it's in potassium 40. But every now and then, a decay will happen in here that changes it into argon. Argon 40 rather, is 18 protons and 40, still has a weight of 40. So one of the protons has turned into a neutron by capturing an electron. All right, I mean, that process by which this happens is not hugely important, but the idea that every now and then a potassium 40 nucleus will become an argon 40 nucleus, it's going to happen at a very fixed rate, a rate that hardworking, dedicated scientists and grad students have spent years narrowing down. We know these rates pretty well. So in this case, potassium 40, K40, is the parent isotope. It's what's decaying into, in this case, argon 40, which is the daughter isotope. Now, in fact, some atoms don't decay at all, or certainly not at rates that we can even measure. Some decay very fast. I mean, some elements decay away in fractions of a second. But for the purposes of dating rocks, we want something that will decay relatively slowly, like over the course of billions of years. The reason why your book likes to talk about potassium 40 and how it decays into argon 40 is there shouldn't be any argon in the rock when it last solidified. Argon is actually a gas. When the rock was liquefied, any gas that was in it would have gotten away, would have bubbled out or whatever. And so in general, we don't expect any argon in the rock. So if we find any argon in there, that is potassium 40 that decayed into argon 40. And so we now know how much there used to be in of the potassium 40, because there's what's ever left the potassium 40 plus the argon 40. That's how many of those potassium molecules we started off with, and some of them have decayed into argon 40. So these happen at very well-known rates. Here's a little graph here where, like, we have these parent atoms. Like, this would be this blue curve here would be the potassium 40 in this case. And at time 0, we had 100% of the ones that we started off with. But in one half-life, we only have 50% of them. Oh boy, the people who are in pre-calc are suddenly remembering this and thinking, oh no, not this stuff. Yeah, half-life. Half-life is how long it takes for half of the parent material to decay. It's a certain number of years, maybe billions. Well, it's a certain length of time. For some, the half-life is a fraction of a second. But for the things that are interesting for purposes of like astronomy and earth science, this is going to be, on the order of billions of years will be its half-life. So over a period of one half-life, let's say it's a billion years, half of the atoms will decay. And then over the next half-life, so now we're at two half-lives, maybe 2 billion years now, another 25% is decayed. Half of what was left has decayed. And then over the next half-life, half of what was left decays. And so on. You notice you'll never get all the way down to zero. But most of it decayed away at the beginning, and then it slowly decays away over the course of many half-lives. Meanwhile, the daughter product, in this case argon-40, increases. At first, it's increasing a lot, and then it increases more and more slowly. But as my 10-year-old noticed as he walked past this board, noticed that at any given place along this graph, the blue curve plus the red curve adds up to 100%. You had a certain amount of potassium 40 at the beginning. Some of it has decayed into argon, but if you add up the argon plus the potassium, it's got to add up to 100%. So we can think about these curves here and realize that if we know the amount of the parent material we started with, and we know the amount of the parent material we have now, well, we could find it on this graph here. Now it's measured, the time units are in units of half-lives. We'd have to know the half-life of the material, but that's the kind of thing labs can tell us. The back of the book or the Wikipedia page or whatever, we can find exactly the rate at which potassium 40 decays into argon 40. Well, then we can find exactly the age of the material. In fact, looking at it on this graph is not necessarily the bestest way of doing it. We can do it using an equation. And you will be using this equation on the lab that you're doing today. Yes, there's a little online lab that we're doing. All right, so there's a little formula here. The amount of time the age of this rock will be equal to the half-life of the material that you're talking about, in this case, potassium 40, and that would be something we'll give you in the problem, whatever, times this fraction. Let's look at the denominator first. The denominator here is the log of 1/2. Now, some people are survivors of classes like pre-calc where we used logs a lot, but they don't necessarily remember it or whatever. Here's the deal. Whether you have seen it before or you haven't, it's not going to be that big of a deal. Log, L-O-G, is a button on your calculator, okay? Or on your calculator app on your phone or whatever. And so experiment with this here. And, log of 1/2 is just some constant. I closed my book. I don't have the page anymore. But in section 8.3, there's a little box on the bottom of a right-hand page that actually works you through an example of this. And it actually shows what the value of log of 1/2 is. Feel free to experiment with that and see if you get the same number they do. Then on the numerator of this fraction here, it's the log of this fraction. The current amount of the material that you are talking about, your parent material, divided by the original amount of the parent material you had. And if you plug all these numbers in here, one big time in your calculator, beep, boop, beep, boop, beep, boop, boop, you will be very unhappy with yourself. You'll almost certainly make a mistake with the parentheses or something like that. It is way better to first compute this fraction up here, then compute the log of it and write that number down, then divide it by the log of 1/2, and then multiply it by the half-life. Don't try to do it all in one fell swoop and then hit equal sign. You'll almost certainly make a mistake with the parentheses or something like that. We're going to be doing examples of that in today's lab, but just to work through a realistic example for potassium 40, let's just say a particular rock contains 0.85 units of potassium 40. I think this actually is the example they do in the book. And we have reason to think it originally contained 10 units of it. Okay, for example, if you added up the potassium 40 and the argon 40 in the rock, it comes to 10 units. So maybe the units are grams or something like that. It doesn't really matter. Okay, well, the only place the argon 40 came from was the potassium 40. So we actually know pretty well how much potassium 40 there is and how much there was at the beginning. And if we plug in there the half-life of potassium 40, which is well known to be 1.25 billion years, well, that's the kind of thing labs do. They figure that kind of stuff out. You can crank those numbers in here. Oh, I made a typo on here. It's 1.25, not 1.26 billion years. But you crank those numbers into the calculation, beep, boop, beep on your calculator. Again, don't do it all in one fell swoop or you'll almost certainly make a mistake. And in this case, it works out to 4.45 billion years. If we had that ratio, we had that much potassium 40 in the rock, and we had, or started off with, if we had currently 0.85 units of potassium 40, and we started off with 10 units, you could do the math, and that rock would be 4.45 billion years old. That would be a spectacularly old rock on the surface of the Earth. Now, this is not a perfect process here. I mean, these equations that describe radiometric dating are actually perfectly fine. There's nothing wrong with that. But like, for example, we'd have to be able to measure that current amount of potassium 40 in the rock extremely precisely. And that is not a trivial thing to do. The potassium 40, it isn't like there's just sort of a chunk of it in there. We scrape it out and weigh it or something. It's incorporated into all these minerals that are in there. I mean, it's just one of the atoms that makes up the molecules that makes up the minerals. It's a difficult thing to measure. And for that matter, figuring out the original amount is a difficult thing to measure, but these are things that scientists do all the time. It is a well-established process on how to do it. Similarly, you have to know that half-life very precisely. Again, that's the kind of thing that you can look up in a table or something like that, or in the case of the lab day I just give you. But I mean, if there was some reason why we measured those half-lives wrong, then we'd be multiplying by the wrong number in here. So, well, as it happens, though, we don't usually rely on just one radioisotope in the rocks, like just potassium 40. Rather, generally speaking, any given rock actually has lots of different radioactive isotopes. Maybe there's radioactive isotopes of iron in there, or gold, or phosphorus, or something like that. And all of those have been studied too. And we know that maybe the phosphorus decays into, I don't know, boron or something. I don't know. I can't think of the periodic table off the top of my head. And we can get another estimate of the age of the rock based on the amount of phosphorus in it. And then maybe we can use some other isotope. And the point is, any given rock, we don't just use one measurement, like just the potassium 40. And then that's actually what you're going to do in the lab days. You're going to use 3 different elements to estimate the age of this rock. And so we very rarely would use just one material in the rock to determine its age. Now, when we actually want to figure out then our plan for, remember the question we're answering here is how old is the solar system? Well, I guess we better start with, we're here on Earth, let's start looking for some really old rocks. That's harder than you would think. We live on a planet with a whole lot of geological activity going on. If you're a survivor of Earth science, you know that the rock cycle is churning. Any given place, you've got some igneous rocks that are being weathered into sedimentary and then being brought in and metamorphosed into metamorphic rocks, which then might remelt and become igneous rocks again. And it's hard. The oldest rocks, like you could actually pick them up with your hand and find, have been dated. They're actually in Canada. Have been found to be about in fact, these are them, are believed to be about 4.28 billion years old based on the isotopes in them. So, all right, that's pretty darn old. We actually can do better than that a little bit. We have found other rocks where some of the crystals in the rocks appear, so not the whole rock, but some of the crystals that were part of another rock originally and then eroded out. We have found some small crystals that appear to be about 4.4 billion years old, which is, not terribly far from 4.28. Oh, except it is like 200 million years different, 120 million years or something. But that seems to be, we keep finding rocks that are about that old. Well, we keep finding, when we find rocks that are spectacularly old, they seem to be in that general range. So we know that the Earth has to be at least that old. I mean, we didn't find the oldest thing on the Earth, right? So, plus, I mean, remember, we're only measuring since the last time those rocks melted. These are pretty spectacularly old rocks, but that they may have melted once before that or whatever. But we at least have kind of capped the minimum. The Earth has to be at least 4.4 billion years old based on these studies of the rocks. We can actually study the rocks that NASA scientists brought home from the moon. In fact, this is literally an Apollo mission in here where the astronaut is out gathering moon rocks that were brought back to the Earth. And in fact, moon rocks all tend to be about the same age. They all tend to be 4.4 billion years old. We haven't talked in this class very much yet about how the moon formed, although we will. If you survived Earth science, you know that we had like a few minutes in that class about how the moon formed. But the fact that the moon would have rocks all about the same age actually makes sense based on what we know about how the moon formed. The moon formed from a collision and everything got all melty and stuff like that one time. And since then, the moon has been dead. There aren't volcanic processes and stuff ongoing on the moon. So again, we think the moon then is about 4.4 billion years old. We're starting to get kind of a sense that things seem to be about that same age. But there are things in our solar system that should be older. Asteroids. Asteroids formed, they're little planetesimals that never got incorporated into other planets. But those little planetesimals formed from, remember the word, the seeds, very early in the history of the solar system. And they haven't changed since. There's nothing going on these asteroids. There are no volcanoes. There's no metamorphic processes or anything like that. The kind of things that happen on the Earth. These things are as dead as anything can be. Any rock that is part of an asteroid is spectacularly old. It is from literally the original nebula that was condensing and collapsing to form our solar system. So this is why we send missions to go get things off of asteroids. The Japanese had a mission called, I don't know how to pronounce it, we'll say Hayabusa, in the early 2000s that kind of failed, but did actually manage to accidentally, the thing that actually was supposed to pick up some rocks there on Hayabusa failed, but apparently, and then when it came back, it didn't have anything. But then they later found that there was like dust and grains of minerals and stuff around it that they were actually able to study from those asteroids. And there's actually a much nicer satellite, spacecraft Hayabusa 2, that is en route back to the Earth now with some rocks off of another asteroid. I can't think of which one that one was. Ryugu or something like that was the name of the asteroid. Anyway, this is on its way back with a load of minerals from that asteroid. And NASA currently has the weirdly named OSIRIS-REx mission, which is just about ready to pick up. When I'm recording this, it's just about ready to start picking up rocks on Bennu, which is a near-Earth asteroid. I say just getting ready to because it isn't like they just sort of swoop in and grab something. They actually orbit these asteroids for literally years before they try to pick anything up because this is a very expensive mission. You don't want to crash. So they get very clear maps of the asteroid before they go and swoop in so that they don't hit anything. Anyway, so yeah, we have had multiple missions where we've tried this thing, and that's cool. We actually, I want to say we don't do that, but we kind of don't need to do that because actually nature delivers us asteroids all the time. And so, well, if we have a meteor that falls into the Earth, okay, well, if it completely burns up, we don't got anything. But if it gets all completely melty falling, well, now we got other issues about things. But if it actually was large enough that it has a interior that didn't melt as part of the process of gliding through the Earth's atmosphere, well, then the interior of that should be spectacularly old. And in fact, when we date them, they're all right around 4.5 billion years old. Few tens of millions of years older than the oldest thing we've ever found on the Earth, which is starting to give us pretty good confidence that we understand what's going on. It looks like the solar nebula was condensing and starting to make these seeds and these planetesimals that later became meteors, and asteroids that became meteors, that became meteorites on the ground. Remember, they're from your grade school science. Meteorites are once they're on the ground. Meteors are while they're streaking through the sky. Well, these all seem like they are pretty strong evidence. I mean, all these asteroids, we always get the same answer. It's about 4.5 billion years ago. These should all be good indications then of the age of our solar system because there wasn't anything, according to planetesimal theory, before all these little, from nebula theory, there shouldn't be anything before the formation of these little seeds and planetesimals and so on. All right, well, that seems like a pretty solid answer then. Could it be that someday we'll find some evidence that contradicts it? That's absolutely possible. It's why we do science. It's why we keep making these efforts and so on. But for now, that is what we've got. And it certainly seems very, very solid. In fact, as your book talks about, this has been tested many different ways over the last 100 years in science, and we keep getting the same answer that the solar system formed about 4.5 billion years ago. In contrast, the universe itself is a little over 13 billion years. Please don't ask me right now how we know that. So the solar system is about 1/3 as old as the universe itself. All right, great. So we have some sense of all of this here. Now, what you're going to do for the lab is you're going to compute how old a particular rock is based on radioactive isotopes. And I'm going to show you that lab in just a second. And then you're going to complete an exit. Let me actually go over here and see if I can find that lab real quick. Here it is. There's not much here. Let's just say we've collected a rock from somewhere. It seems to be particularly old. It's not the oldest rock on Earth or anything, but it's pretty darn old. And it contains three radioactive isotopes. There's an isotope of iron that's going to be decaying into something. I don't bother telling you what it is. There's an isotope of nickel. We'll say whatever it is. And there's an isotope of carbon. And in the problem, I give you the half-life of each of those materials. They are all completely made up. I just played with numbers on a spreadsheet till I got the answers I wanted. I did not bother looking up real isotopes or anything like that. Then basically you answer the same question three times, but first time you're going to use iron. Here it is, iron. There's currently 1 gram of it in the rock, and based on the amount of the daughter isotope in the rock, we know that it originally contained 10 grams of this isotope of iron. So you're going to go back to that equation. You're going to plug in that it currently has 1 gram. It's originally had 10 grams. Its half-life is 1 billion years, and you'll go beep, boop, beep on your calculator, and you'll get an answer, and you're going to put that answer in here. And I'll tell you in advance, just as a clue, it is more than 3 billion years. Okay, it's like 3.4 or something like that, 3.4 billion years or something. All right, then you're going to repeat the same calculation using nickel. And I'm telling you here that there's currently this many grams of nickel in there, and that we know that there should have originally been 15 grams of nickel in that rock. And the half-life of the nickel is given up here someplace. Here it is, 5 billion years. And you'll do the calculations, and you won't get exactly the same answer. But it'll be, within 1 or 2%, maybe, I don't know, maybe 10%. I forget it. They're in the ballpark of each other. And then you do the same question again, but this time for the carbon in the rock, where we say there's this many grams of carbon in the rock, and we know that there should have originally been this many grams of the carbon, and you've got the half-life of the carbon up here. No, where is it? Up here. And then you plug those numbers in, and you'll get a third estimate of the age of the rock. And again, they better not be spectacularly off. They should all be within a few percent of each other. That gives us some confidence that we know how old it is. I mean, you can well imagine that in the real world when they do this, sometimes there's an error in measurement or something like that. And maybe the iron is way off from the other two in terms of its estimate of the age. Well, that's why we have multiple ways of missing the age. Okay, apparently we did something wrong with the iron. There was some data problem. In fact, I give you a space here to tell me what you think could have gone wrong on this as to why they are. That comes from this lecture here. We had a slide where we talked about the kinds of things that can be wrong, that are sources of error in this calculation. All right, that is it. That's all we need. I wanted you just to work on this. Again, this is not some huge thing. It's actually very close to things that they did in pre-calc. If you took that, although I don't expect you necessarily to remember how you did it, I'll be glad to give you any help you need if you're having trouble with these calculations. And take care of yourselves out there, and let me know if you have any questions.